Hi guys, in this video we'll pick up here with the Williamson ether synthesis. And I will do this one at the bottom. We have this phenol with the acidic OH, acidic enough to be deprotonated by hydroxide. Okay. As shown just above. This substituent here, this ether substituent, this methoxy group is just going to be a unreactive substituent in this reaction. The hydroxide will deprotonate the phenol and convert this to the phenoxide. I don't need to show a mechanism. I'm asked to show a final product here. This is a predictive product reaction. The KOH is going to give me the phenoxide. I can just do that. Okay. Potassium plus. Now we come in with a carbon with a leaving group, tosylate, and we can do a classical SN2 reaction. And so now these electrons attack the carbon. We do have a chiral carbon here. That's a deuterium. In organic 1 we mentioned deuterium. Isotope of hydrogen, but the leaving group is the tosylate group, electrons on to oxygen, SN2, and we can show the product. It's going to be this oxygen now bonded to that carbon. That carbon has an ethyl group. Okay, I can do this. I can put the ethyl in the yes, how am I going to show this chiral carbon? I'll put the ethyl group in the plane, and then the deuterium that's on that carbon also, it will be, I can show that forward. And there we go. Instead of a tosylate on that carbon, we now have the oxygen on that carbon by an SN2 substitution reaction. And SN2, of course, comes with inversion. And we have inversion here. We can check that. Oxygen 1, 2, 3, deuterium, H in the back. This is S. Now, this only works if the new group is the same priority as the leaving group, and indeed it is, oxygen. 1, 2, 3, H in the back, and indeed this is R. That doesn't prove it's inversion. Inversion comes from the fact that I see that the groups are this way, and when the nucleophile came in, the groups went that way. I'm seeing that. It is inverted. Keep in mind the leaving group here is in the plane. Okay. We talked about some of that in Organic 1, how to deal with inversion. As opposed to just kind of memorizing some tidbits that don't always work. Okay, Williamson ether synthesis. The phenol, instead of an OH group, the oxygen is now an ether. Okay. But let's look at synthesis, going backwards. How would you synthesize this ether here? Choice of route is important. It's actually called methyl tert butyl ether. Used to be used as an oxygen additive to gasoline, but no more. Now ethanol is used. Let's think about this. Let's go backwards and let's use a retrosynthetic arrow. A double-lined arrow means we're going backwards. If we broke this bond, let's call that A, we would go back to this alkoxide. That looks a little funny. Can I make that an Me? Okay, like a methyl group. That's the way I typically do it. Go back to that oxygen anion. Because remember, Williamson ether synthesis involves, okay, an anion reacting with a carbon with a leaving group. So when we go backwards, we want an oxygen anion and a carbon with a leaving group. The carbon would be here, and we can put a leaving group on that carbon. What's your favorite leaving group? How about a bromine? Okay. We could take that back and say, theoretically, we could react this here and come this way would be an SN2. We'll have to come back and analyze that. The other bond, oxygen-carbon bond we can form here is here. Let's call that B. This is A. B. Let's go back to this oxygen anion. Plus just a one carbon. It's hard to draw a one carbon. One carbon with a leaving group. Well, we can stick with bromine. Again, that looks a little funny. We can call this a CH3 bromine or a methyl bromine. A one carbon with a leaving group. Which of these two reactions going this way looks best, makes the most sense, or would be highest yielding? Well, if you look at A, we have a problem here because the leaving group is on a tertiary carbon. And you don't do an SN2 with a leaving group on a tertiary carbon, right? That is not going to be a good reaction. We would not want to propose that reaction. The better reaction will be having this alkoxide react with methyl bromide. These electrons attack, I've got a generic methyl here, that's a CH3. I don't really like doing that. I'd rather be a CH3 drawn there. I'd rather not do chemistry with abbreviations. But kick off the leaving group. That looks pretty good. Leaving group is on, that's not even a primary carbon, it's just a methyl. That's going to be a good, and so this is the reaction we would propose. That will be the best, the highest yielding reaction. The highest yielding Williamson ether synthesis. That route is best. Okay. Why don't you try the next one on your own? Doing a similar approach, A and B, because there's two different oxygen-carbon bonds you could form, theoretically. Okay, also for homework, explain why the Williamson ether synthesis below is not logical. What product is formed instead? All right. So analyze this reaction, see what the problem is, what product is formed instead. Note, thioethers, okay, can also be made by the Williamson ether synthesis. Instead of a phenol or an hydroxyl group, sulfur below oxygen in the periodic table, we can have an SH called a thiol. They're actually more acidic than alcohols, corresponding alcohols. And so with hydroxide, we can deprotonate it. You know your acid-base mechanism. I'm just going to show a deprotonated, okay? That's called a sulfide, okay, with an anion. Now we come in with a carbon with a leaving group. These electrons attack and kick off the chlorine here. Sulfur now bonded to the CH2, and it's got a cyano group. The cyano group is not the leaving group. The chlorine is. And we made a thioether, which that is also called a well, it's called a sulfide. Yeah, that would be called a sulfide anion. Even though it's got the "ide" ending, it's still neutral here. Usually "ide" endings are anions, but that's called a sulfide there. Or thioether. And if you remember in the functional group handout in Organic 1, I believe we called these thioethers. Okay. All right, Williamson ether synthesis. Next, reaction of ethers. All right. We're actually in our outline. We finished substitution, elimination, and O-alkylation. We're not going to do oxidation of alcohols quite yet. We're going to skip to chemistry of ethers, and we're going to look at dealkylation or cleavage by using acid and a nucleophile. Two different pathways, theoretically. Somewhat like a reverse of a Williamson ether synthesis. Except here we've got acid. We're going to have cations. Dealkylation or cleavage of ethers using HX. Okay, we'll see that it gives an alcohol plus an alkyl halide. This is about the only reaction that ethers will undergo is to break them apart, cleave them. Let's do the first reaction here. Let's just see what we can do. We have a strong acid. We got a Br minus. We can just show that ionized. We've got an oxygen. What can you do here? The only thing you can do is protonate the oxygen. The Br minus is not going to do anything here. Protonate the oxygen. All right. Just like protonated an alcohol. You know, make it more generic. Protonate the oxygen of an alcohol, protonate the oxygen of an ether. Really no difference. Now the oxygen can be a good leaving group. Now the bromide can act as a nucleophile. Okay. But the oxygen can leave two different carbons, either the carbon on the left or the carbon on the right. If we had only an alcohol that was protonated, okay, there's only one place for the bromide to attack. It's only one carbon. You have to attack here and kick the leaving group off of that carbon. But when you protonate an ether, you have two different carbons you can attack and kick the oxygen off. Are we going to attack over here, which by the way is a tertiary carbon, or are we going to attack a primary carbon? That's actually not a primary carbon, is it? That's just a methyl. primary carbon is bonded to one carbon. This is not bonded to any carbons. So it's not even primary. Well, we have a rule. When a tertiary reaction site is present, always go SN1. If no tertiary site is present, go SN2. All right. Keep in mind that a resonance stabilized secondary carbocation is just as stable as a non-resonance stabilized tertiary carbocation. That's something we can refer back to later. It's an important statement. Okay, do we have a tertiary site? Yes, on the left. So we're going to go SN1. That means the bromide would never attack here because you don't do SN2 at a tertiary carbon. Instead, SN1, which involves the leaving group just leaving. And that gives a tertiary carbocation plus the alcohol. It's just methanol. Can I draw a methyl or a CH3 on the end? Just to clarify that that's methyl group. I always like to do that. Okay. Lone pairs, of course. All right. That was actually the leaving group. That whole molecule was the leaving group. Now the Br minus can attack tertiary carbocation. It's really trigonal planar. I don't have good bond angles there, but it attacks that. And that gives that there. And those are your two products. Okay, we cleave the ether to, what did we say it would give? An alcohol and an alkyl halide. Two smaller products from a larger starting compound. Okay. Almost like the reverse of a Williamson ether synthesis. To come back to the ether, you're going to have problems here because it's the leaving group's on a tertiary carbon. But I was going to say you deprotonate the alcohol and then you have the oxygen anion come in here and kick off the leaving group. It's not going to be so easy to go back from these two. But these are the cleavage products of this ether. All right. Let's try the next one. Looks very similar, except on the left it's a secondary carbon. What can we do to this ether? We can protonate it. That's it. Is it okay if I just protonate it and not show that mechanistic step? Now, if you were asked to show a mechanism, you would want to show every single step. But in terms of the lecture, we can just say it's the same as above, right? Protonate it. You know how to protonate an oxygen. We have a Br minus. Now, do we have a tertiary site? No. If no tertiary site is present, we want to go SN2. Now, if you're going SN2, which carbon are you going to attack? The methyl carbon or the secondary carbon? SN2 is largely governed by sterics. SN2, you're going to attack the least substituted carbon, kick off the leaving group, and that will give directly your products, SN2. Up here it was a two-step SN1, two steps after you protonated. SN2 gives that alcohol, which was actually the leaving group, and a bromine attached to the methyl, which in some cases just may be called methyl bromide. Okay, you can show it variety of ways. I showed out the carbon. And so in this case, you get the OH ends up kind of on the substituted fragment, okay? Because we did an SN2, we attacked the least sterically hindered site. All right. For homework, do this reaction of ether with HX. Okay. What if we had a cyclic ether? The oxygen is part of a ring. Well, it's very same chemistry, very same mechanisms. An ether with strong acid, we can protonate the ether. Again, I'm not going to do a mechanistic step. All right. Now we have a choice. Do we have a tertiary site available? No. Secondary over here, primary over there. There's no tertiary site, so we're going to do SN2. Cl minus. SN2 would involve reacting. These electrons attack the least sterically hindered site and kick the leaving group off of that site. That would be here. Kick off the oxygen. And SN2 gives, I'm going to draw this, boom, very similar to how it's drawn here. The oxygen and the H get kicked off. Let's show lone pairs if we'd like. Boom, boom, boom. Here's that carbon there. What's now bonded to that carbon? Chlorine. Let's make it look nice and pretty with lone pairs. There's your product. It's no longer an ether. But the alcohol and the alkyl chloride are within the same molecule. We didn't make two different molecules like we made above because the original was in the ring. And so they remain bonded to each other up through here. Now let me ask, can this react again with HCl? It actually could. We could protonate the alcohol. I'll do that since I don't want to mess up our pretty looking product. Let's redraw it protonated. Now we have Cl minus remaining. Can this act as a nucleophile and kick off this water? Yeah, what type of mechanism would we do? SN1 or SN2? Those are your choices when you have a tetrahedral carbon with a potential leaving group. That's a secondary. What do you do with secondary? Is it going to be SN1 or SN2? It could actually be either. I would tend to go with an SN2 and give a product that looks like, let's see, that's going to be boom, 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 boom. chlorine would be here, and the methyl group would be pushed to this side. And so I just did SN2 with inversion. All right. Plus water in this case, which was our leaving group. So actually this ether reacted with 2 equivalents of HCl, and oxygen served as a leaving group twice. Now this could also do SN1. SN1, I'm not going to do mechanism, I'll show multiple arrows, which indicates there's multiple steps there. I'm not going to say how many. I don't want to clarify how many. The difference is, if it was SN1, the product would be, we would lose our stereochemistry. And this would now be racemic, right? I would probably go with SN2, and actually if you use this rule up here, there was no tertiary site available, so we went with SN2. But you got to be careful here. If we're doing a pure predict the product, I would probably say go SN2. But you need to be alert to maybe you'll see it as an SN1, you know, and you would say, huh, it must have been SN1 if it's racemic. So it's good review there. All right. Now the one below, all we can do is protonate the oxygen. Now, do we have a tertiary site available? No. Primary, that's a benzene ring, and so it's a secondary carbon here. But this is where I said keep in mind that a resonance stabilized secondary carbocation is just as stable as a non-resonance stabilized tertiary. And down here, I would probably expect this to go SN1, this to leave. If you want to draw that benzene ring out, okay, we abbreviate benzene ring as phenyl, pH. Not the same as pH with acid-base chemistry, but that would leave a carbocation here, yeah? It is secondary, but it's resonance stabilized. Look at that. That's probably what I would predict, because again, when the carbocation is resonance stabilized, it sort of bumps it up a notch, like from secondary to tertiary. Then the Br minus can attack here to give our product OH. How many we got? 1, 2, 3, 4 carbons. 1, 2, 3, 4 carbons, and then the benzene ring. And the bromine is here, and that's a chiral carbon, but it would be racemic, right? Because when nucleophile attacks the planar carbocation, it attacks from either side. Now, this could theoretically react again with HBr. All right. because alcohols can react with HX. I only did that one time. Actually, up here, these alcohols could also again react with HBr. But I just assumed one equivalent. Here I showed you two equivalents of this strong acid. Okay, how about this one here? This cyclic ether, 5-membered ring with no substituents, is called Tetrahydrofuran because if you had two double bonds, that's called furan. We'll see that when we do aromatics during test 2. But if you hydrogenate both double bonds, 2 H's added here, 2 H's added there, that's 4 H's. Now you have tetrahydrofuran. That's actually a common solvent in the lab. What if we reacted this with a strong nucleophile with no acid? And it doesn't matter that it's THF. This could be any ether. It could be any of these up here. What if you reacted these with a strong nucleophile and no acid? There would be no reaction. Because the only way to get the oxygen to leave one of the carbons is to make it a better leaving group. And with the ethers, the only way you can do that is to protonate them with strong acid, which includes possibly a Lewis acid in advanced cases, but for most of what we look at, we're talking about strong proton acid. All right, so here's what we can say. Ethers are only cleaved under acidic conditions. Under neutral conditions, or under non-acidic conditions, ethers are not reactive, including basic conditions. If you're under basic conditions, ethers are unreactive. That's one reason that ethers make good solvents for highly basic reactions, because you don't have to worry about your ether reacting. They'll only react, the oxygen will only potentially leave under acidic conditions. Okay, so ethers such as THF or diethyl ether, okay, which you saw in the nomenclature most likely, and I think we've used diethyl ether in the lab, much more common. Okay, good solvents for highly basic reactions. An exception to this general note is epoxides. An epoxide, we will see 3-membered ring oxygen, cyclic ether. These will react with strong nucleophiles under basic conditions. Okay? That's because of the ring strain. And we will cover those in a different handout. All right. So cleavage of ethers. All right, that's the handout here. Chemistry of alcohols and ethers. There's warm-up page. Okay. You know, this is really just a Williamson ether setup. Question though is, which alcohol or hydroxyl group is going to be deprotonated by the sodium hydroxide? This reaction may be in the workbook. Okay, nomenclature. All right, this finishes up this first handout. We'll see what type of questions come up, and we'll do a couple of the homework problems during the lecture time.